So this video is going to explain some of the basics of acids and bases. So before we even started this, you probably have some idea in your head, some memory of what makes an acid and what makes a base a base. We're going to start to build on that. So you may remember, for example, that acids give foods a tart or sour taste, right? There are a lot of common foods that have acids in them. There are also dangerous acids that we use more in the laboratory, but there are also more common acids that are not as dangerous, though we're going to talk about what they all have in common. So acetic acid in vinegar, that's essentially what makes vinegar vinegar, is that acetic acid. And if you can remember the sour taste of vinegar, that's from that. Citric acid in like lemons and limes, for example, is another example of a common acid. Tannic acid is commonly found in tea. And vitamin C is actually more formally referred to as ascorbic acid. So it's actually another kind of acid and something you take all the time. Another kind of acid you might have in your soda is carbonic acid, from that dissolved carbon dioxide forming an acid, and also phosphoric acid are just common acids that are found just in soft drinks. So if we look at these examples of acids and their formulas, you probably start to see a pattern emerge, right? And so you probably realize that that pattern is that there's an H on the front. So let's take a look at, there was a scientist named Arrhenius, and he gave an initial definition of what he thought an acid was. So in order for something to be an acid, it has to have at least one acidic hydrogen, an H+, when dissolved in water. So in other words, when you take the chemical, like hydrogen chloride, which is actually a gas, and dissolve it in water, for it to be an acid, it's going to have to break an H+ off of it and leave behind the anion, in this case a Cl-. So that's going to be generally what makes something an acid, is if it has that H+ that it's going to dissolve and break off, essentially. So if we look at some common reactions of acids, one of the famous ones is acids with metals. So acids will react with active metals like zinc or magnesium to produce hydrogen gas. Here's our generic formula, so you just want to get familiar with these generic terms. So M is for metal. HA is the generic expression for an acid. H literally meaning hydrogen, because it's going to have a hydrogen at the left of the formula. And A just standing for the generic anion, whatever that hydrogen is attached to, that when the hydrogen leaves, it will become a negative anion. So A for anion. And what we're seeing here in this reaction is that the metal will actually bump out the hydrogen atom, and so what you'll have be left behind is what's called a salt, or an ionic compound is just another name for it is a salt. In this case, we're going to be forming, the metal is going to be essentially bonding with the anion now, and what's left behind is however much hydrogen gas that was made. So now specific examples of that same general equation are if we react magnesium with hydrochloric acid, it's going to make magnesium chloride salt and hydrogen gas. Zinc with hydrochloric acid will make zinc chloride salt and hydrogen gas. So that's what we see. We see that when a metal reacts with an acid, it's going to produce hydrogen gas. There's going to be a bubbling. And if you were to hold a match over the reaction, it would actually be popping, because that's traditionally what happens when hydrogen's being reacted with under the flame, is a popping sound. And we could also kind of predict this. I mean, this looks probably, hopefully, really familiar to you. Like, what type of reaction is this? If you look at the types, like single replacement, double replacement, synthesis, decomp, combustion, this is a single replacement, because if you remember, these couple of metals are actually above hydrogen on our activity series list, and so they would actually bump out the hydrogen, make a new compound, and leave behind an element, a diatomic element. So we don't really have to learn anything new here. This is just a specific example that applies to acids, but this is just a single replacement type of reaction that we've learned. Another famous reaction of acids is how they react with carbonate. They react with carbonate, which if you remember is CO3₂-, to form carbon dioxide, water, and a salt. So, for example, a lot of historic buildings are made of structures with carbonate in them, so they actually react to acid rain, and it actually wears them down slowly. Old gravestones and things like that also react with acid rain through this general reaction. Now, calcium carbonate is found all over the place. It's found in chalk, it's found in seashells and eggshells, in tums. So that's a lot of places where calcium carbonate can be found, and this is the reaction of that with hydrochloric acid to make, again, carbon dioxide, water, and a salt. So that's what will always happen. Acid plus carbonate makes carbon dioxide, salt, and water. Another way to think of that too is that this is only going to happen with carbonates because the carbonate, the CO3 2-, is providing the C and the 2 O's in order to make CO2. We couldn't have seen that with the previous reaction. There's no oxygen present and no carbon present, so it wouldn't be possible. But it's possible here, and you probably did this reaction last year in biology. This is the egg first placed in vinegar, and what the purpose of that was to get the eggshell to react and go away so that you could do your osmosis lesson. So this reaction is here where calcium carbonate is the eggshell, acetic acid found in vinegar is the acid that you reacted it with, and it formed the bubbles were carbon dioxide, and it left behind a salt, in this case calcium acetate, and water. So notice that both of these are forming the same products, it's just that the salt is different. But the CO2 will always be exactly the same, and the H2O will always form in this kind of reaction. So we can expect that. So we can predict those products essentially. The only thing that we wouldn't be able to have memorized is the salt part. Okay, so switching gears a little bit to bases. Now you may have some memory of what makes a base a base. They taste bitter, they feel slippery, and examples of them are sodium hydroxide, like what's in lye or drain cleaner, milk of magnesia, which is magnesium hydroxide that's used to treat heartburn, again to alleviate that acid, ammonia, which is in Windex, and calcium oxide, which is used to neutralize acidic soil. So here's a bunch of examples of bases. And again, hopefully you start to see a pattern here of what makes a base a base. And so according to Arrhenius, what that was is that a base will produce hydroxide ions when dissolved in water. So if we look back, Arrhenius said that an acid will produce H+ when dissolved in water. A base will produce OH- when dissolved in water, or hydroxide. And here's our generic equation. So those hydroxides are pretty much always a metal attached to OH-. So here's metal attached to OH, and in water that will break apart into M+, right, the positive cation metal, and the anion will be hydroxide. That's what makes it basic. And our real example is sodium hydroxide dissolves in water to break apart to form sodium and hydroxide, the hydroxide ion and the sodium cation. Before we take another definition of what acids and bases are actually more thought of today, we need to take a look at the hydrogen atom, because we've been talking a lot about hydrogen, right? And we need to really take a look at what all this means. A traditional hydrogen atom, the most common isotope of hydrogen, will have no neutrons, right? So it's number 1 on the periodic table. We're literally talking just a proton and an electron. But we're not just talking about hydrogen, we're talking about H+. When you remove that electron, you're just left with the hydrogen nucleus, right? And it just so happens that for hydrogen, the only thing in its nucleus is a proton. So what that means is that hydrogen ion, H+, is the same thing as just a proton. So from here on out, we're going to be calling this a proton, and we're going to be using it in the language of acids and bases. Sometimes you'll hear H+, but just know that they're interchangeable. A proton is an H+ ion, because hydrogen, if you remove that one electron to make it from hydrogen to H+, all that's left will be a proton. So in acid nomenclature, when you talk about it, we're talking protons pretty much. Okay, so now that we took a look at that, there were a couple other chemists who developed a little bit further their definition, and their definition actually encompassed Arrhenius' definition, but then it also added these other parts to it too. So they actually broadened the umbrella to accept more chemicals as acids or bases, while still accepting Arrhenius' definition. So our generic equation, acid, H+ in the front, and then an A attached to it just means anion. That's all that it means. So this is our generic acid. You'll see a lot of this. It looks like laughing, but it's the generic formula for an acid. So H attached to A. And here's our generic equation. It reacts with water to make, this is a new term. This is important. This new term over here is called hydronium, Hydronium. So we made hydronium, and then we leave behind the anion. This you really have to take a close, careful look at to see what happened. What occurred was the acid gave away its proton, its H+, and water picked that up to make H3O+, and the negative anion. So this was what was left over when the acid lost its H. Our real example here is hydrochloric acid, reacts with water. Notice how it makes it an acid because it gives up its proton, gives it to H2O. H2O becomes H3O plus with that additional H, and what's left behind is the Cl minus. So in other words, according to Bronsted-Lowry, we're broadening this and we're saying that an acid is something that will donate its proton. We called it a proton donor because it's giving away its H+. So the acid will be the one throwing the football pretty much. Now our new definition for a base that still gets us to produce OH- in general is that we're saying the base is a proton acceptor. Here's our general formula. Base plus water, for example, gives you the original base. It picked up an H+, and it left behind an OH-. For now, just focus on the fact that acids are proton donors, bases are proton receivers. So that's what's going to make the difference there. And again, this is just re-emphasizing that. Arrhenius had his definitions, and then the Bronsted-Lowry theory expanded upon that to say, okay, we're going to include all those, but also we're going to say that acids are a proton donor, and bases don't just produce OH- when they're dissolved, they also accept H+. So we have a broader definition now. If you want to pause the video, take a closer look at these, you can, but this is what we just mentioned. While we're talking about that, we need to talk about conjugate acids and bases. So remember, a Bronsted acid is a proton donor, gives up its H+, and a Bronsted base is anything that's going to accept that H+ into its formula. So in our formula here, we have water reacting with NH3. Now if we look to the right, we see what happens that changed is that water gave up its H+ to NH3. So that means that water was the proton donor, the acid. Water can be like an acid, and NH3 acted as the base because it accepted that proton. If we look at the opposite side, we have what are called their conjugates. So on the left side, H2O gave up its H+, this is going to be important to understand, and became OH-. But if we go the other direction, from right to left, going from right to left, OH- is actually picking up an H+, it's accepting a proton to become water again. So going on the other direction, that's acting as a base. So what we call the acid-base conjugate pair are H2O and OH- in this case. H2O from left to right gives up an H+, becomes OH-. From right to left, it accepts that H+ and becomes H2O. So that means it's acting as a base going from right to left. So it's its conjugate, con meaning with, they act as a pairing together. Now NH3, initially going from left to right, is accepting the proton and acts as a base. But if we go from right to left, the NH4 plus that formed is actually giving up its H to go from NH4 plus to NH3. That is also a conjugate acid-base pairing. This was a base initially. Its conjugate acid, or the acid that it became, is this. So this is how we pair them. This goes with this. This goes with this. The only change between them is the number of hydrogens, number of protons, pretty much, that they're swapping. Okay. This is seeing some more of that, essentially. So going from left to right, HCl is the acid because it gives its proton to H2O. And then conversely, if we went the other direction, H3O plus, hydronium, if you remember, is the acid, gives its H plus to Cl minus if we went the reverse direction. So acid, base for accepting the proton, conjugate acid, because this was a base, this becomes its conjugate acid, and this is a going the other way, this would be the proton acceptor, so this would be the conjugate base. Over here, we see H2O giving away, it's being a proton donor, so acids for H2O in this case, bases NH3. And then we kind of see the pattern going on there. Notice how on the bottom reaction, we see that water can give an H plus or receive an H plus. Water is amphoteric. It can react with acid or base, is what that term means. Okay, so as far as what they have in common, they both cause indicators to change color. So they both they both cause indicators to change color. The colors will be different, but they both cause the change in color. Litmus paper will turn red for acid, and if it's blue, it'll turn red. If it's red, it'll stay red. Blue litmus paper will stay blue for base, or if it's red litmus paper, it will turn blue. So whatever, acid will turn things red or stay red. Base will turn litmus paper blue or stay blue if it's already blue. Second thing they have in common, they are both electrolytes, meaning when you put them in aqueous solution, they both conduct electricity. So that's what we see over here, lighting that light bulb. They're both electrolytes, something acids and bases have in common. Finally, they both neutralize each other. So they both neutralize each other. An acid reacting with a base will produce salt and water. Remember, salt being an ionic compound. If you look at our formula over here, this is again something we've seen before, so it's kind of convenient. This is a double replacement reaction. Na swapped with H plus. And so if you also think about it another way, the acid gives up its H plus, its proton. The base gives up its OH minus. When H plus finds OH minus, they become H2O, and they form a salt. This is literally salt, but also an ionic compound generally is salt. So these are the things we need to be aware of. One of the only things we didn't mention separately is that, of course, acids have a pH lower than 7, and bases have a pH greater than 7. And you remember neutral water has a neutral pH of 7. But this is a good review. It's good to pause and take a look at this if you need. This is also reiterating what they have in common as well. So this is a lot to digest. A lot of this was review. So I recommend kind of pausing, taking notes, or just taking this a little bit at a time.